Hello everyone. Today we'll be talking about our quantum reinforcement learning project, which is about a multi-agent QRL approach for GPS denied path planning. As we all know, path planning is really used everywhere, from maps, from navigating till my home till university, everywhere. Path planning is the foundation for mapping or any sort of thing. But now the problem is what exactly happens in GPS denied environments. Obviously, GPS can be denied in multiple areas, starting from indoors to even the zigzag tunnel in Cornish. All these places actually do not really support GPS. But what exactly happens in tunnels or anything of this sort? Challenge is these when these GPS signals falls for a long period of time, then we won't be able to navigate on our own. So autonomous vehicles actually find this as a problem because they have to navigate it without the help of GPS. So robots actually need to learn how exactly to navigate through it instead of just relying on outside trained data on a new environment. It won't really be feasible. But this becomes actually hard when you add like multiple robots into it, considering that the multiple like vehicles and you shouldn't actually hit them, considering them as obstacles. So this can be used in normal navigation of a navy, or it can also be used in like disaster prone systems for like multiple robots scanning the whole environment. Now, this can be used in search and rescue, like I've just told, or like warehouses, tunnels, deep sea exploration, multiple areas where GPS can be denied. Now, the big question is why exactly use quantum computing and why are we integrating reinforcement learning into it? Now, a fascinating thing is this has never been worked before where we integrated QRL with GPS path planning. And if you notice, this can also be the novelty of the paper, and we're trying to bring in new concept for the first time. So reinforcement learning, as we all know, if an agent does any good work or if a model is good, we reward it. If it does something bad, then we penalize it. Now we take this whole thing. It resembles how we do for quantum computing, where we have a lot of dimensionality, a lot of Hilbert space, a lot of states in Hilbert space. So when we actually take these multiple possibilities and put them in Hilbert space, it actually fits in the perfect definition for quantum computing. And these small stuff can actually represent a complex system. And that is the beauty of how the path planning works. So with obviously quantum circuits, we can use entanglement and superposition to find out where exactly the position is and how exactly to navigate through it. That is why we've taken hypothesis of how quantum computing can be integrated with reinforcement learning. Now, we have taken a hybrid approach because a classical system is used for processing the data and clubbing it together, the sensors, the buffers, and everything that's happening in classical systems. But quantum computers, obviously, since they're still in their NISQ era, they have limitations to overcome still. So we cannot rely completely on a quantum system. So we made the decision making part to be the quantum system so that we simulate circuits and make it adaptable for the environment. So we have taken a classical environment in agents. We've taken the data classically, processed it quantum way in a variational quantum circuit VQC, decoded the action back into a classical system. Now, within the VQC, we have upgraded each round using parameter shift optimization, and there's always a fallback mechanism to this. Now, how exactly does quantum work in this? So we've taken every single classical state vector, which is from the data itself, and we have converted into rotation kits, Rx, R by RZ. And this is loaded into the system into qubits, multiple qubits, and then it's processed into the VQC. So the VQC or the variational quantum circuit actually takes the agents and it takes all these rotations into weights so that we can train the model and we can fit it in such a way that it actually updates based on these weights. And there's obviously entanglement and superposition involved in this entanglement so that the networks have actually correlation. This is for the agentic part to know the position of one another. So this is a sample diagram showing how the data is classical, taken converted angles and then to qubits and then passed through the circuit. And we have taken the decoded it back to classical methods. So a big question now arises. How exactly do we tell it to move correctly 170 degrees or to move it front and right? A bit like that. So we have taken two qubits here in this example, where two qubits can represent four states at once and give probabilities of them, where we have taken 0001, 10, and 11. So each of these represent forward, left, right, and backwards. Now here backwards represents weight because we cannot really go backwards on a highway. So this is just an example, but the actual system has been trained on multiple stuff, multiple qubits, and in total there are 8 qubits we've trained on, so that we make sure of every single angle that we're taking care of. And here we've implemented a stochastic sampling so that the highest probability, that is, if up is the highest probability that is moving forward, we don't just take it. We sometimes take the even worse option so that we can actually go depth wise and explore it beforehand before actually going through the whole solution, so that the exploration can happen simultaneously from the quantum principles of superposition. The whole simulation is as follows. So we have a grid. Here, a grid is used for hardware constraints because we cannot really simulate a complex environment. We have placed obstacles, we have placed restricted zones, and some collision risks with other agents that are on standby, and some penalties so that we can get efficiency. Now, this principle is repeated every round, and we have updated our policy gradient so that we can gradually learn after each round how the results are, and we reward based on that. Now, the multi-agent part is so that the agents don't really like fumble with each other and interact with each other to give a better result. So each one of the agents shares their input, shares their output, and which is taken by the other agents as the input. These observations actually help avoid collisions and other harmful stuff that might happen while you're on road. We The fallback system is based on the Q-learning module, which is already inbuilt, and this is running parallelly just so that there's always a fallback mechanism if the quantum system actually fails. Now, some of the results here are we have obtained a 94.3% accuracy here compared to all other methods. We've obtained a significant improvement, and we've given a better average reward compared to the other methods, that is classical DQ and A-star search Q-learning. Collision rate has been significantly decreased, and the GPS noise tolerance level has been significantly increased. All this actually represent that our system is performing way better than the existing solutions, despite being a new hardware constraint method. This is because a quantum method actually encourages exploration all at once, and that is the one conclusion that we have derived from this. Next thing is how different noise levels are being impacted, how the accuracy is dropping at each noise level. So from 0% noise, we can see that the accuracy is dropping from 98.7% to 84.2% at no GPS. So this shows that we've actually gone a lot of accuracy drop between the noise levels, and it can actually impact us a lot. But this also shows that there's a potential improvement and because we can't just collide on things. Okay. So some of the conclusions are obviously we have implemented a hybrid QRL system, which consists of multi-agents to ensure the navigation is done correctly in a GPS-denied environment. Some of the key achievements include whatever we have implemented so far, and also a novelty on how this has never been worked before. And we've proven that quantum methods are actually superior to classical methods in this. So it can be a possible future direction. And another key achievement is that we have submitted this paper to ICML workshop, and hopefully it gets accepted soon. Thank you.